Hi, in this video I'm going to talk about the conservation of momentum, okay? And so I'm going to use some examples first. But before I do that, let me just write that F net times T equals change in P, okay? Now, momentum is conserved if there is no change. That's basically what it means. So this delta P has to be equal to 0, okay? If momentum is to remain conserved, meaning like it doesn't change. Now, if delta P is equal to 0, well, time cannot be 0. It just means that F net is 0. So in order for impulse to be conserved, there should be no external impulse. And I'll explain what external impulse means. Now, I'm going to write another formula that I didn't talk about in the past. So I'm going to say F net times T is equal to P final minus P initial. Okay, I'm going to rewrite this differently. So this is the external impulse. So I'm going to write that as PF equals, or let's put it this way. I'm going to write PO plus external impulse equals PF. I'm writing the same thing, just rearranging the terms. Now, if there is no external impulse, this becomes 0, okay? Which means the initial momentum is equal to the final momentum. Okay, now let's do some examples and let's see what do we mean by no external impulse. So I'm going to do some examples here. So I'm going to write PO plus J external equals PF. And since this is one-dimensional, I'm not going to put the vectors. I'm only going to do this in one dimension. So let's say we have two objects, object 1, object 2, and they're going to collide. Or maybe they go in at each other, they go in, one is going to rear end 2, 2 is going to rear end 1. It doesn't matter. So let's just say they move in this direction at first, right? And the 1 is going faster than 2, so it's going to hit it. So if we look at the system as a whole, meaning like 1 and 2 together, when that collision happens, that's not an external impulse. Why? Because that's an internal interaction between 1 and 2. So we say that the momentum of the whole system, 1 plus 2, is conserved. So how do I write that? Well, let's say this one had a velocity v1, this had a velocity v2, and let's say they both move in this way. Okay? Well, you know what? Let's just put some numbers in there. How about that? Makes it easier. So let's say this is going at 10 meters per second. This is going at 2 meters per second. This has a mass of 5 kilograms. This has a mass of 10 kilograms. Now, how do we write the conservation of momentum? Now, if the interaction between them is internal, there's no external impulse, which means the momentum before the collision must equal the momentum after the collision. Well, let's do the momentum before the collision. I'm going to look at right as positive. This has a momentum of mv, which is 5 times 10, that's 50, plus this has a momentum of 10 times 2, which is 20. Now, the collision happens, okay? Now, let's say the 5 kilograms maybe bounces back with 1 meter per second, okay? The 2, we have no idea what happens to it, okay? Obviously, it's going to continue to the right. That's common sense. But we don't know how fast it will be moving. Well, we do the conservation of momentum again. Okay, so the momentum before equals the momentum after because the interaction is internal. Now, it is going to be 5 times 1, but that's a negative 1. So that's negative 5. Plus, this is a 10 kilogram. 10 times, let's call this V2 prime. Prime means later. V2 prime. So if we do the math here, what do we get? 70, 75. So V2 prime is going to be equal to 7.5 meters per second, which makes sense. Now, how does it make sense? Well, the momentum of the 1 by itself is not conserved. The momentum of the 2 by itself is not conserved, but the momentum of the whole thing is conserved. Well, the 1 will definitely either be going slower than 10 and continue in the same direction, or reverse direction. So it's not conserving momentum. The 2, okay, will be definitely going faster than 2 meters per second, and it is. So again, why isn't the momentum of this conserved? Well, because there is an impulse on it from this 2. Why is the momentum of this not conserved? Because this one is hitting it. So there is an external impulse on it. But as a whole, that interaction between them is internal. So that's one. So let's look at another case where maybe this guy is going this way at 2. And guess what? When they collide, there's some damage, but they're gonna become 1. So it's gonna be a mass of 15 kilograms. And we wanna know how fast is that mass going and in what direction. Well, momentum here is 5 times 10, that's 50. Okay, plus, that's 10 times negative 2, that's negative 20, equals, now they become 1. Okay, so the mass is 15. Well, since they became 1, I don't know which way they're going to be going, so I'm going to call that V prime. Could be right, it could be left, V prime. And I'll let the math tell me which way it is. So that's 15, so that's 30. So V prime equals positive 2 meters per second, which means they're going to combine and go to the right. And you could have seen that coming before you even do it. See, the momentum of this is more than the momentum of that. This is a 50, this is a 20. So this one is winning for sure. So this one is going to force everything to go to the right. Now let's look at the last case. Let's instead of having them stick together, let's say they were stuck together like an explosion. Okay? And maybe they were moving at, let's say, 3 meters per second. And the explosion is going to happen. Well, actually, let me do an example where they are at rest at first. Okay, so here is the 5 kilograms, and here is the 10 kilograms. Let's say the 5 goes this way at 1 meter per second. What is the speed of the 10? So let's call that V2 prime. Well, the momentum here is 0, equals 5 times negative 1, that's negative 5, plus 10 times V2 prime. Well, V2 prime is going to be equal to what? 5 divided by, so 0.5 meters per second. Okay? So we can say that since the momentum here is 0, the momentum, overall momentum, the total momentum has to be 0 here, which means that the momentum of this mass and the momentum of this mass are equal but opposite. Okay, so let's look at a last case where, well, maybe they are moving at 3 meters per second, and the collision happens. This one does not have to go back. Let's just say maybe it's going forward at 1 meter per second. Can it be going back? Probably, but I don't know that. So let's look at the momentum of this. That's 15 times 3, that's 45, equals. Now the momentum of this is 5 times 1, because I'm told that this one is going to the right. So it could be bouncing back because of that explosion. And that explosion is internal. That's a force that happens between the parts of the system, which is the 2 masses. So that's 5 times 1 plus 10 times V2 prime. Now V2 prime, if I do the math correctly here, should be 4 meters per second. Okay? Yeah. Okay? And it kind of makes sense if you think about it. This one has to go faster because it's experiencing a push from this guy. So it's going to be going faster than 4. And that's pretty much conservation of momentum and talking about systems. So yeah, the momentum in a collision, the momentum of the whole system is conserved, but the momentum of the parts, of each part, is not conserved because there is external forces on it. So the question you have to ask yourself is, when this collision or this explosion happens, is there a force acting on whatever you consider the system? If your answer is yes, then the momentum is not conserved. If your answer is no, the force or the interaction is internal, then yes, the momentum is conserved. And that's pretty much conservation of momentum in a nutshell. And we'll do some practice, and you're going to see that this is actually an easy part of momentum. It's all linear. Okay? All right. Thank you.